Oh, cool. Cool. So real quick, I didn't picture you writing this part down. It's just for more setting the tone for kind of the stage for our conversation today. But we know about voltaic. We know about voltaic cells. They're spontaneous, so delta G is negative. Describe the battery or the cell to me. Oh, these got nasty. Two separate containers connected by salt bridge. Yeah. The big difference for electrolytic is that it's all in one pot. It's all in one pot. Actually, you can have it all in the same container because we're actually forcing the electrons to go where we want them to go. So that, I think you already have the stuff on the left. We've seen a number of examples for the stuff, and that's where I don't anticipate you writing on that one. Just general reminders here. So for voltaic, these are spontaneous. They're going to do work on the surrounding. They give us electrons. When we turn our power button on our phone, it turns on, lets us send our snaps. Yeah.
So an electrolytic cell requires a voltaic cell in its power supply.
We need direct current from somewhere else, yes, to actually make it go. Now, usually we're using the plugins, and so that power is coming from the burning of coal, turning boiling water and turning a turbine. Except for in Missouri, I think we're 45% nuclear. It's the same process. Yeah, we're getting electricity from spinning a magnet and a big copper coil. But you're right. Yes, you are still applying electrical energy. It's just you are putting it into the system instead of it coming out of the system. But all the same stuff is happening in the same places. Oxidation is happening at the anode. Reduction is happening at the cathode. It's all the same reactions. It's just taking place in one pot. The big difference, if you notice, is that the signs switch. The signs switch. And the reason for that is what happens at those spots. No. Because really what this is describing is where we're actually sending the electrons. We're using the power supply to actually send the electrons to the cathode. So now we got extra electrons over here. What gets attracted to the, well, yeah, all right. Positive gets attracted to the negative, right? So the B plus comes up, grabs that electron to turn into, right, reduction, gaining electrons, turning into B. And so we end up seeing as we see plating occur, just like we saw in our Fedi lab, when we put the copper in, whoop, and we plated the zinc ions to our cathode. What happens at the anode? Oxidation, which is the lost electrons. So the A minus gets attracted to the positive electrode here. The A minus hits this metal, gives away one of its electrons. It gets taken away, whoop, up into the power supply. And then we make A. So we actually get plating on both. And this is actually how, like, when I pay a company, I pay Flint Scientific to give, like, send us things like sodium metal. You can't, like, that's not a thing you can find in nature. Sodium only has one valence electron. It gives it away. It's super reactive. It's all in a compound. And so we actually use electricity to make the sodium metal. Then they sell it to me. They ship it to me. And then I throw it in water and it turns back into Na+. But we actually use electricity to make that process happen. How done? Electrolytic? There's a lot more details here, but we've said it. Cool. Yeah, so if you're taking notes, I'd start here. So for our electrolytic cells, they're just non-spontaneous. We got to put energy in. Now, good news, everyone. You already know how to find that voltage, right? How do we describe how well we attract electrons? The E, the cell potential. It's just when we do the math, it's going to be, E's going to be negative, which is telling us, the sign just tells you that's how much energy you got to put in to actually get the reaction to go. It's the exact same math. We're just going to have a negative number, and that's the voltage we got to either meet or exceed to get the reaction to occur. And so here's an example of how we can actually use our two electrodes to make our tin chloride come out. So we get pure tin metal plating on the cathode, and we actually get chlorine gas starting to eke out on the anode, and then now, yeah, cause internal bleeding if you were to breathe that in. Good old mustard gas. It's not technically. But this is how we get a lot of our elements. It's also how, for my guys, sorry, but you get the cheap Claire's jewelry. That's got the thin layer of nickel on the outside, and then it's like copper in the core. No, I'm getting no head nods. Nobody's had it where like the ring wears off a little bit and you can see the copper on the inside. Right? It's the same process they use to like plate a lot of our different metals as with our electrolytic process, just like we did with the pen. I'm glad we did that. It's good to reference. Good reference, buddy. Cool. Yep. So wait, yeah. Here's some practical applications: electroplating, separation of elements, separation of ions. I just said that. You got it. You got it. Cool. Just some general notes. I would get these. Electrolysis does use a direct current. We're gonna plug in. We usually use a voltmeter or a power supply to actually change the amperage. We'll talk more about that here in a second. Amps. Yeah, we're just forcing the electrons to go where we want to go. Big difference is your cathode is the negative terminal. It's the source of the electron. It's got extra electrons hanging out there. Your anode is the positive terminal. The electrons are moving away from it. That's why we see the ions move the way we do to those corresponding electrodes. I'm gonna just put them all up. Anions flow to the cathode? Nope. Anions to the anode. Excuse me. Cations to the cathode. We end up seeing plating out on both. We're still oxidizing at the anode. We're reducing at the cathode. Same process. It's just where the different ions coming out. You do sometimes have to crank it. Called an overvoltage. Sometimes you have to put a little extra oomph in to actually get it to start the process, but then once it's going, you can kind of back off again. Activation energy. Sometimes you just need good wires. I struggled for a long time to get the Penny Lab going because we just had bad alligator clips. Finally went to physics and he had the good ones. Amazon. Oh, sorry, I should be careful. There's some examples in here. I don't know if this is helpful for us to see them compared graphically. I don't know if this is helpful for us. But this is, if we're thinking about our signs for a voltaic or spontaneous, the free energy is negative. It's got energy to lose. For your cell potential, it will be a positive cell potential. Remember, those are inversely related. Inversely related. But everything's still happening in the same spots. Oxidation at the anode, reduction at the cathode. And then we give a negative sign for voltaic, negative sign on the actual anode when we label our diagrams. We have a negative sign for the anode, positive sign for the cathode. The two things that flip then for electrolytic are G and E flip, because it's non-spontaneous. Delta G is positive, greater than 0. Cell potential is negative. Got to put energy in to get it to go. Everything still happens in the same place. We just change the sign to help us know where the ions are going to plate out. Lets us know where those ions are going to plate out. And what if it's at 0? What if E cell or G is 0? You're at equilibrium, K equals 1, and your battery is dead. You got no more free energy to do work. Gotta go plug your phone in. It would be, so at 0, when delta G is 0 or E cell is 0. So if they both get to 0, your battery's dead. There's no more free energy available and you got to go plug it back in. really, you take your voltaic phone that normally goes on its own, you plug it in so that the voltage in the plug can recharge or change it back into electrolytic. Then you unplug it, it goes back to voltaic. It's both. Switching between the two. Right. AP, yeah. AP. 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 Why not come on? It's been fun. It hasn't been fun?
It's been fun, but
Hasn't been real fun. Been real, it's been fun, hasn't been real fun.
no, it's real fun, but.
Yeah, it is tough.
Thanks, my GPA.
It is tough. Alright. We know enough, we can actually talk about how much is gonna play it out. And this is kind of our last topic, is how we actually quantify the amount that's gonna come out. You're gonna love it. It is stoichiometry. It's just dimensional analysis. I left the mole train up for you. It's great. Yeah. Yep, I'm gonna skip through the example. Because we already talked about it. Cool. Faraday's law of electrolysis. Faraday's law of electrolysis. Hang in there, almost done. Almost done. I know. End of the day Friday. Hang in there. You can do it. The amount that plates out, the amount that you get is directly proportional to the amount of charge we're putting into our cell and the amount of time that we're running it for. There's kind of the two big factors when we start to think about how much we're going to actually see plated out. Faraday's law, the amount of substance produced at each electrode is directly proportional to the quantity of charge flowing through the cell. Yep, I'd be willing to bet Faraday's constant's coming and roaring back again. It's Faraday's law. And a reminder, Faraday's constant is just the change in charge when you move a mole's worth of electrons from one beaker to another. So we have a way to kind of quantify the amount of change in charge that's happening when we start moving those electrons around. That's Faraday's constant. Yeah, there's really kind of three questions I can ask. I don't know if you need to write these verbatim. I wouldn't. If I was taking notes, I wouldn't. There's three types of questions. How much you're gonna get? Grams. How many grams? Gonna play it out. How much charge do you need to get the grams you want? Or how long is it gonna take you? That's pretty much it. Those are the three types of questions I can ask when it comes to our electrolysis calculations. So how many grams? How big a charge? How long is it gonna take? We do have to talk real quick about amps. I don't get real bogged down in it, but we do need to talk about how amps are measured. Amps, amperes, AMPS,
I
amps,
figured that out.
amps,
Thanks.
amps. How long? What amount of time? Yep. Cool. So here's your steps. You got to balance your half reactions to solve for N, number of moles of electrons. You're gonna need to know Faraday's constant. Sorry, it's rounded here. Faraday's constant, which is the charge per mole of electrons. That sure looks like a conversion factor. Yeah. And you probably need to know the molar mass. This formula down here at the bottom, this is how we get kind of our charge and our time put together. So amps is the units that we use to measure the current. And usually you would actually set on your power supply, you do a little box and say, I want to do 4 amps. That's the amount of current I want to put into my solution. You actually get variable supply powers that can control the amount of amps going into the solution. And it is just a measure of how much charge is going into the solution per second. That is how we define an amperage. Amperes. So it's just the charge, which is coulombs. Hey, coulombs. Oh, coulombs. 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 Per second. Yeah. Yeah, so the shorthand amps is I, is the symbol I. So it's gonna be coulombs per second. Charge. What is that like? Is that how it is on the grid sheet? Q over D?
Yep.
Nah. Nobody tells you, like Q is charge in coulombs, D is time in seconds. Oh, it is, yeah, I equals Q over T, that's right there. Right there. Ooh, the Nernst equation's still on there. I didn't know. I took that off. Yeah, on this again, sorry, good, sorry. Sidebar, there's a section on Nernst equation, concentration cells, don't worry about that, we didn't do that. Not responsible for that. All right, just a couple examples, we'll call it. All right, ran away. No, you're good, no. Yeah, there's a lot of rain. I'm gonna do it right. Bell rang, it's like, oh no. In the words of my brother, nobody died. My brother's a civil engineer. He's like, yo, Mr. Jorgensen, you have a bad day, you make a mistake, you just fix it. Like next day you teach it right, own your mistake and fix it. If I have a bad day, nobody catches my mistake, my building collapses and I kill thousands of people. It's like, so I think about that. I think about that sometimes. Like, well, yeah, nobody died. We're okay. We can fix it tomorrow. Yeah, we're all doing our best. Teachers make mistakes. Yeah. 2 areas human. Think you're gonna like it. Think? We'll find out. I guess we'll find out. How long does it take to produce 3.0 grams of chlorine by electrolysis using aqueous sodium chloride with a power supply with a current of 12 amps? Think of it like 2 problems. Because what formula has time in it? How long that's time? How long that's time resolve the time? Which formula had time in it? Yep. R I equals Q over T. Sorry, we said amps equals coulombs per second. So I think eventually we gotta get here, right? But think of that as a separate problem. What was your given here? We got 3.0 grams of chlorine. This is what we want to make, right? We're gonna shoot a bunch of electricity in here. We're gonna cause an oxidation reaction to occur. What's floating around in what's in the beaker? Sorry, what's floating around in the beaker?
CO.
We got Na plus and Cl minus. Okay, what's the sodium gonna do? Gonna gain an electron, turn into sodium metal. All right, we're shooting electrons in. And then what's chlorine gonna do? It's gonna try to lose an electron to go from Cl minus to Cl2. Ooh, but wait a minute. To make Cl2, you need 2 of these, and you need 2 electrons. Sorry, 2 negatives, which means we multiply this by 2, yeah? 2 Na plus 2 electrons making 2 Nas. The only reason we care about this is for N. What's N? N equals 2 moles of electrons. In order for our chlorine to come out, we gotta shoot at least 2 moles worth of electron in for every mole of chlorine gas. This is how we find our N. Oh, okay. Change your grams to moles. Mole mass,
9.
9 grams per 1 mole of chlorine. It is straight up strike, which is nice. It's a fun kind of like bookend. It's nice. And then we know per mole of chlorine that we make, we need how many moles of electrons? There's our N. Per mole of chlorine gas that we make, we need 2 moles worth of electrons. Ooh, and then we know that per mole of electron, that takes a current or a charge of 96,485 coulombs. Faraday's constant. Whoosh, whoosh, whoosh. All the coulombs. Underneath them? No, you're guessing. I get.
8200.
Wait. 82.
00.
0. Awesome.
82.
I just want to miss a 0. I don't miss a 0. All right, hey, now we know our coulombs. Did we know our amperage? Yeah, we set it at 12 amps. Let's just plug it in. We got 12 coulombs per second. That's just A, right? Units on A. I'm just showing you that the units work out. We got 82,000 coulombs worth of charge going in. We're solving for seconds. Coulombs cancel. Ooh, seconds is in the denominator. That would be the reciprocal, right? Sorry, would you rather this be X? We'd multiply X up and then divide the 12 over, so I think 8200 divided by 12. Huh?
Would that be 11.3 minutes?
Oh, okay. All in minutes? You can leave it in seconds, doesn't have to be minutes.
23 seconds. 11 minutes, 23 seconds.
What's the number in seconds?
6.
Yeah, 680.
608?
No, 680.
80, thank you. Either of these would be appropriate.
Like, yes.
Your stick pick would be enough. Sorry. Another example? Yes, no? We're good? One more? Let's do one more. All right, let me go back. Questions on what we did? Can we wait full 30 seconds? I can do it. It's a long time. All right. Yeah, let's do one more. Actually, on Friday. Reverse, reverse. Well, not really, I guess. We're still giving grams, right? We got point. All right, my markers. My marker. We got 0.86 grams of chromium. Oh, yeah, what's going around? We got CR 3+ and SO4 2-. Oh. Oh. Let's see. Yeah, it's gonna have to be 6, isn't it? Yeah. It's chromium. It's, oops, sorry, can gain 3 electrons, turn into CR. Problem is, we don't know what the SO4 is gonna turn into, do we? Cause it might turn into SO3, yeah. Or just S, yeah, we don't know the other oxidation number, but if this is a 2 minus and this is a 3 plus, we would expect it to be 6, and so we would multiply this all by 2. It'll be clear on your examples. The problem is we don't have enough information on this one here. Yep. Alright. Given the grams, what can we solve for? Okay. This is fun because we know that for every 2 moles of chromium we make, it takes 6 moles of electrons, which is gonna reduce to what? 3, yeah. That's fun.
It doesn't matter.
It doesn't matter. And we know per mole of electrons, Faraday's constant, 96485 coulombs. Two zeros?
Yes.
Awesome. That's coulombs. We know coulombs, we know kind of time. The problem is amps is measured in coulombs per seconds. So we gotta change this into seconds.
750,
750? How'd you do it?
60.
That number times 60? Oh, yeah, okay. We want to solve for amps, yeah? It's just charge over time. Huh?
A lot of amps.
There's a lot of amps. That would shock you. That one would hurt. We got some additional sample problems on the back of the handout from yesterday. So questions 5 through 14, answers are all on there. Monday, quiz in class. Your brain, your pencil. I want to see how we're doing. Nope, not that one. It is shorter. I shortened it because of the eclipse, right? Eclipse on Monday. That's why I will not be here. I'm taking the boys. We're gonna get to the path. Yeah. Yep, 3 multiple choice, 3 calculations, 3 golden oldies. Hey, if you're sorry. If you think about calculations, probably gonna be one from the triangle, couple from the triangle. And then there's probably gonna be 1 plating question. I just want to see if you can do it. I want to check before we get to the test. And then there's 1 golden oldie. There's 1 golden oldie. It is Hess's law. Here's your stuff. Yeah.
Oh, wait,
Hess's law.
can it be,
Wait, is
wait,
that
extra
delta
credit?
or delta?
Delta H, enthalpy.
Can it be 3 extra credit?
Round law.
Maybe. We'll see.
And that's the one I-
Oh, can it still work? Oh, no, that's okay.
Salutation, reduction potentials, finding E cell. Writing your half reactions, balancing redox. And then we got our calculations using spontaneous formulas, G, K, and E cell. Okay, I'll be done. Time's yours. Either ask questions from the homework. Ask the questions from the homework or you're asking questions from the lab. Time is yours.